G'day everybody. In this video lesson we're going to look at the rules for integration. Integration being the opposite process to differentiation. We're going to start by looking at some basic polynomials. How do we find integrals of those? What other rules do we have for integration? That's going to include rational functions, power functions where we've got square roots and so on. That could be trigonometric, exponential. We're going to deal with most of those. That will take up most of the time in this lesson. This lesson will actually be in two parts. The second part, which will be shorter, we're going to have a look at finding an actual antiderivative, which is an application of integration, and we'll have a quick chat about what's the difference between an indefinite integral and an antiderivative. Often the two terms are used interchangeably, but there is probably a subtle difference between them. We're going to look at a lot of examples during the course of this lesson. So because it's a topic that you probably have seen before and have some idea about, for any examples, if you think you can do them, it might be an idea to stop the video and see what you already know. Come back to the video and check your solution. Before we look at examples, here's our list of rules that are given to us in the VCE Math Methods formula sheet. So we've got a rule for x to the power of n. That expands to a rule for ax plus b to the power of n. Here we've got our rule for exponential functions, e to the ax. When we've got 1 over x, the integral of that is the log of x. And we're going to look at one or two examples where we have a trigonometric function. So let's start off with something very basic, the integral of x cubed with respect to x. So I'm just using that first rule that we looked at a moment ago, x to the power of n, so n is equal to 3. That means in this rule n plus 1 is 4. So we've got 1 over n plus 1, or 1 over 4, x to the power of 4 plus c. Or that could be written as x to the power of 4 divided by 4. Those two expressions are basically the same thing. Here we've got the integral of a squared factor. So we've got 2x minus 1 squared. I'm actually going to look at this problem twice. Here's our first solution, and you can see that I have expanded that because it's fairly easy to expand. It gives us this trinomial where we've got three separate terms, and when you've got separate terms that are separated by addition or subtraction, you can find integrals of those individual terms. And so the integral of 4x squared is 4x cubed over 3. Integral of 4x to the power of 1 is 4x to the power of 2 over 2. Here's our pattern, 3 over 3, 2 over 2. The integral of 1 is equal to x. It's a very simple integral, but it's one that sometimes students overlook. And there's our constant of integration. One of those terms can be simplified, so 4x squared over 2, we've got negative 2x squared. And that's our simple integral, indefinite integral. I've solved this one a different way. The second rule in that list of formulas is where instead of x we've got ax plus b to the power of n. So we've still got 1 over n plus 1, but in addition to that we've got 1 over a, ax plus b to the power of n plus 1. So in this case, ax plus b is our 2x minus 1 pattern, and n is equal to 2. So there's our 1 over a, n plus 1, a plus b to the power of n plus 1. Our constant of integration, And when we've got 1 over 6, we can either write that as a coefficient or we can divide the expression by 6. Either way, they are the same. Here we've got a power function, square root of x. It's called a power function because we can write x to the power of something to represent that, which is necessary either if we want to differentiate or integrate an expression like this. So remembering those index laws, such as this one up here, the square root of x can be written as x to the power of a half. So we've got the integral of x to the power of n plus 1 becomes 3 over 2, 3 halves. And our 1 over n plus 1 is 1 over 3 over 2, which we've got, we're going to use the reciprocal of that denominator, which is just 2/3. So we've got 2/3 x to the power of 3 over 2 plus c. Here we have a rational expression again. If this is something we can write as x to the power of n, then we have a simple rule for finding its antiderivative. So 1 over x squared, using this index law, can be written as x to the negative 2. When n is equal to negative 2, n plus 1 that we use in our rule is negative 1. So there's our 1 over n plus 1, x to the n plus 1. And our indefinite integral is negative 1 over x plus c. This one looks like it's a rational function, but we need to remember if it's something over x, we're going to have a rule, a particular rule for this integral. So there's two things going on here. For a start, if I can see a constant factor of my function, I can take that factor out the front of the integral, and sometimes that makes what's inside the integral a little easier to work with. So in general, and this is not written on the formula sheet, it's something you should practice and remember, if the function has a constant factor k, we can take k out the front. So we're left with the integral of 1 over x. Sometimes students think, well, let's write that as x to the negative 1. If you try that, you'll find it doesn't really get you anywhere. We do have a rule for 1 over x, and that is the log of x. So we've got 3 times the log of x plus c. There's our rule down here that comes from the formula sheet. Let's have a look at an exponential function. So the rule that we're using with this function, we've got an e to the ax type of expression. So our integral will be 1 over a, e to the ax. In this case, a is 3, so we've got 1 over 3, e to the 3x. Always include the constant of integration. There's a little bit going on here. We've got a rational expression where we've got x in the denominator, but x is part of e to the something. We've got an exponential part of this. We also have a fairly awkward sort of coefficient here to think about. So let's break this down. For a start, this 1 over 2, or this 2 in the denominator, we can see that that's 1 over 2, or just a half. That's our constant k that we can take out the front of that integral. Then we're left with e to the 3x, which is in the denominator. We can write that as e to the negative 3x. And now we have that e to the ax pattern, where a is negative 3, not positive 3, but negative 3. So using that same rule we used in the previous problem, here's our k, here's our 1 over a, e to the ax plus c. When we tidy that up, we can leave the power as negative. We can have negative 1/6. Or we can have e to the positive 3x if I put it in the denominator of that expression. And we've still got that coefficient at negative 1 over 6. Now, one other important rule to remember, and I say remember because this is a rule that's not going to be written on the formula sheet. If we are aware of basic rules of integration, so just where we've got something simple like e to the x, 1 over x sine x, if we already know what that integral is, then the same rule applies if we've got not x but ax plus b as our input for that function. The only difference being that when we write the integral we include this coefficient of 1 over a, where a is that coefficient of x. So if we already know a simple rule for f of x, we can apply the same rule to f of ax plus b if we remember to use the coefficient 1 over a as the coefficient of our integral. So let's have a look at an example of that. So here I've got 1 over 4x minus 3, and we can see that ax plus b pattern at 4x minus 3. We're going to relate that to the simple function 1 over x. We know that the integral of 1 over x is log of x. So if I've got 1 over ax plus b, then the integral of that will be the log of ax plus b, but we include this coefficient of 1 over a. So if the integral of 1 over x is the log of x, then the integral of 1 over 4x minus 3 is the log of 4x minus 3, and we include 1/4 as the coefficient of that integral. Same constant of integration. With this particular rule for a logarithm too, we have this specification that x is greater than 0 for this formula. In this case, that means that 4x minus 3 must be greater than 0. And that sort of corresponds to where that asymptote is for a log function. If 4x minus 3 is greater than 0, it would follow that x has to be greater than 3/4. So that's the condition for this integral, that it works for values of x that are greater than 3/4. And you can see down here, if 4x minus 3 is greater than 0, x must be greater than 3/4. So I'm going to just wrap up part 1 there, and as I said, part 2 is a much shorter video lesson. When you watch that second part, I'll get you to then fill out the Google form, log your attendance, and review both video lessons in that Google form. Thanks very much.